Okay, so today my goal is to talk about computing using stochastic logic. We have spent a lot of time talking about 2's complement arithmetic. We have seen how computations like multiplications can be computed using 2's complement arithmetic, using numerous approaches such as modified Booth recording, Wallace tree, and other number representations such as carry save and redundant number systems. So in 1960s, there was some effort to implement circuits using so-called stochastic logic, and the idea is that computations are not exact. They are probabilistic. So in some sense they are probabilistic, and that's what is called stochastic logic. So the first thing that we can think about in a stochastic logic representation is that, so let's just begin with the thought process of a unary number. So when we think about a 2's complement number, that's called a weighted binary representation. So in a 2's complement number, or just even think about a non-signed number. In a non-signed number, if I have 1, 0, 0, 1, and that's going to be equal to 8 plus 1. The weights of these are 1, 2, 4, and 8. So that weight is 9. That the weight of the next most significant is twice the current significant. In a unary number, all positions, this is not a weighted representation. All positions have same weight, and that is called a unary number representation. So for example, 1, 0, 0, 1, using 4 bits, I would call this 2 out of 4. So 2 by 4 or half. Why 2? What does this 2 mean? That's the number of non-zero bits. So you count the number of non-zero positions is equal to 2. Total length of the bit stream is 4. So the value of the number is 2 by 4. So if I have 1, 0, 0, 1, 1, 1, 0, 0, 0 as an example, in so-called stochastic representation, I will talk about 2 types, unipolar and bipolar. That's same as unsigned and 2's complements in standard representation. But let's stick with unipolar, what I would call unipolar, which are positive numbers. So this would be how many non-zero bits? 1, 2, 3, 4. How many total bits? 3, 6, 9. So that would be 4 by 9. So in a unipolar, we'll talk about what that means. In a unipolar stochastic number, lies between 0 to 1. Okay. So we describe this as a probability. That's why the probabilistic computing, as we will see, leads to the name stochastic. And unipolar means these numbers lie between 0 to 1. Now, in contrast, we can also think about these stochastic numbers to be bipolar, where they lie between -1 to 1, and these are signed numbers. And in this case, if you take the unary bit stream, so in case of unipolar, 0 is 0, 1 is 1. In case of bipolar, if you take the bit stream, unary bit stream, 0 means -1, 1 means 1. So what would this number be in bipolar? If I take that number, if I take this number and think of that, so in unipolar, that's in unipolar. In bipolar, so how many ones? 4 ones. They add up to 4. How many zeros? 5 zeros. Each zero is a -1. So 5 zeros are same as minus 5 divided by the length 9, and that's going to be minus 1 by 9 in bipolar. So the same bit stream, there is nothing different, same bit stream, but when represented using unipolar has a value 4 by 9, when represented using bipolar stochastic number representation, it has a value minus 1 by 9. So if a certain bit is 0 or 1, if a certain bit is 0 or 1, so unipolar, bipolar. So unipolar 0 matches to bipolar minus 1, unipolar 1 matches to bipolar 1. So in general, if I think of this as a variable x, this is a linear mapping. So we are taking the dynamic range 0 to 1. Well, let's take it here, 0 to 1 in unipolar, and we are mapping that to a, so this is the unipolar range 0 to 1. We are mapping that in the bipolar case to the range minus 1 to 1. So the 1 goes to 1 and 0 goes to minus 1. And in general, any bit x will map to 2x minus 1. So 2 times 0 minus 1 is minus 1. 2 times 1 minus 1 is plus 1. Any value x will map to a value, and x does not have to be 0 or 1. X is the unipolar value. So for example, if I go back to our example, 4 by 9. 4 by 9 in unipolar will map to 2 times 4 by 9 minus 1, which is 8 by 9 minus 1, or minus 1 by 9. So any unipolar value for a certain bit stream, we don't care what the bit stream is, but if the value is x, the bipolar value of that same bit stream is going to be 2x minus 1. So that's that's basically the number representation of unipolar and bipolar stochastic number representation. It's a linear mapping. So if I have a number p in probability, we call that probability because in the unipolar representation, the number lies between 0 to 1. So every number between 0 to 1 can be thought of as representing a probability. So the p would represent 2p minus 1 in bipolar representation. Now what if it was a p in bipolar? What would that mean in unipolar? So if I knew that the bipolar value of the number is p, so in other words, if I knew that this number is minus 1 by 9 in bipolar representation, what would that be in unipolar? Well, that's going to be p plus 1 by 2. Okay, why is that? Well, the way we, so you just, okay, let's call 2p minus 1, let's instead of calling this p, let's call this x. So start with this p. So what is this p? P is equal to x plus 1 by 2. And that's how we can get this p plus 1 by 2. Replace x by p. And indeed, if you multiply this by 2, the 2 cancels out, and then minus 1 is back to p. So if the bipolar number is p, unipolar number is p plus 1 divided by 2. If the unipolar number is p, the bipolar number is 2p minus 1. Okay, so we have talked about the very basics, and the reason there was a lot of interest in the 60s, 1960s, computing resources were very limited. And that's the reason every multiplier was implemented by an accumulator in the microprocessors. Okay, and so a lot of the signal processing functions used to be implemented using bit serial arithmetic because there were not that many resources. So it so happens that stochastic logic is another way to implement functions using small number of resources. So for example, if I want to multiply two numbers x1, x2, so if I want to multiply two stochastic numbers x1, x2, then I can simply multiply them by an AND gate. So y will be x1, x2. So that's kind of surprising that I don't need a whole multiplier. And we'll talk about the drawbacks. Obviously, there are many drawbacks. If indeed the stochastic number solved a lot of the problems with respect to area and energy consumption and so on, this would be in every computer, but that's not really the case. But nevertheless, I think there is interest in learning about stochastic logic. It has a lot of different applications, and in fact many useful applications. Useful, not in terms of designing a CPU or designing modems and communication functions and so on, but there are cases where this might be useful. And so let's talk about if I had a number x1 and a number x2, these are stochastic numbers, then what would be the output of the AND gate? Okay, the AND gate is, the output of the AND gate is 1 if the two inputs are 1. Okay, so let's, before I talk about y is equal to x1, x2, let's just take some example here. Let's take that example I had, 1 0 0 triple 1. So let's just say 1 0 0 triple 1 0 0 0, and let's say 0 1 0 1 0 1 0 1 4 and 1. Okay. So if I have these x1 and x2, these are 9-bit representations. What's really the output? 0 times 1 is 0, 0 times 1 is 0, 0 times 0 is 0, 1 times 1, that's 1, first one, then 0, another 1, 0, 0, 0. Okay. So this number was 4 by 9. This number is 1, 2, 3, 4, 5. 5 by 9. And this number is 2 by 9. What would be the real result? 4 by 9 times 5 by 9 would be 20 by 81. 20 by 81. Which would be 2.22 goes on 2 by 9. So if I divide 9, that's 2.22, 22 all the way. If I write that as 2.2 by 9, and instead of that exact result, we get an approximate result. It's not exact. So this stochastic computing is not deterministic. It is computing in an expected sense. So what we are really computing is y in an expected sense. What does that word even mean? So that means if the value of x1 is p1, let's say x1 represents a value p1, x2 represents a value p2, then expected value of y is going to be p1, p2. So y is not going to be exactly x1 times x2. If I experiment with millions of values of x1 and x2 and compute the output y in the expected sense, output will be P1 times P2. Okay, but it won't be exactly P1 times P2. So if you think about, okay, we'll talk more about how the error can come down or the standard deviation can come down. We'll talk about that, but for now let's just talk about why it is P1 times P2 or y is equal to x1, x2. So the probability that y is equal to 1 is equal to the probability that x1 is 1 times the probability that x2 is 1. And if I assume that probability of x1 is 1 is P1, so that means although it is true that it has a lots of zeros and ones, but ideally speaking, all I'm trying to say is that the probability of 0 is 0 and probability of 1 is P. Probability of 1 is P. So this is going to be P1 times P2. But really, this is in the expected sense. So this is in the expected sense. So if you think about what is going to be the, so if you think about the expected value of y to be 1 is so y is either 1 or 0. So if I think about x1, x2 and y, so let's talk about x1. So if I talk about x1 having a probability P1, so that means probability that any bit, the probability of any bit being 1 is P1, probability bit being 0 is 1 minus P1. So the expected value of x1, if you think about this as a Bernoulli random variable, then that's going to be 1 times P1 plus 0 times 1 minus P1, which is going to be P1. Now if you try to compute the expected value of x1 squared, that's also going to be P1, which means the variance of x1 is going to be P1 minus expected value of x squared minus mean squared, P1 minus mean P1 squared, which is going to be P1 times 1 minus P1. Okay, so so that's the variance of a Bernoulli random variable, which is P1 times Q1 or 1 minus P1. Now, if this is the probability of any bit, and if I assume length of the bit stream to be L, then the value of x, expected value of x1, so let's say that expected value of x1 is equal to summed over I equal to 0 to L minus 1, x1, expected value of x1i. So if x1 is represented using L bits, L unary bits, like here. So if x1 is represented using L unary bits, and each bit probability of being 1 is P1 and 0 is 1 minus P1. And that is going to be sum of the expectation is expectation of the sum. So that's going to be equal to P1. So this has to be divided by L because I need to add all these quantities and divide by L. So if this thing is P1, P1 times L divided by L is P1. What is going to be the mean squared expected value of x1 squared? Expected value of x1 squared is going to be, now we will assume each bit to be independent. That's a big assumption. Each bit is independent, and that's sometimes that will not be true. But if I assume that, if I make this independence assumption, then this is going to be 1 over L times summed over I equal to 0 to L minus 1 expected value of x1 I squared. Okay, so this is going to be, what will this quantity be? So if this is going to be x1 is 1 with probability P1, so this quantity as I calculated here is going to be P1 so P1, so this is still going to be P1 exactly as I calculated here. P1 added L times divided by L times, which is going to be P1. No, this is actually not true. So let me just write down, let me write this down. X1 is equal to x1 0 plus x1 1 plus up to x1 L minus 1 divided by L. So if you take the expected value of the squared, this is going to be 1 by L squared times the expected value of these squares plus the cross products x1 x0 x1 x1 0 1 1, and those are all independent, and because of the independence assumption, okay, so I think I should probably be a little more careful. Okay, so let's see. So x1 squared is equal to x1 0 squared plus x1 1 squared plus x1, let's just take three possible values, squared plus 2x1 0 x1 1 plus 2x1 1 x1 2 plus 2x1 0 x1 2 divided by, let's take L equal to 3. So L equal to 3 is 9. So this is the expected value of this whole thing, and that is going to be, these values will be P plus 3P. So 3 of these will be 3P plus these, each one of these is going to be, these are independent, so this is going to be expected value of this times expected value of that. So this is going to be 6 times P squared, 2P squared times 3 divided by 9. Okay, in general, this is going to be L times P plus L squared minus L times L minus 1 times P squared divided by L squared. So that's going to be the general value, and the variance of x1 is going to be expected value of x1 squared minus expected value of x whole squared, and that is going to be L. So LP by L squared is 1 by L times P plus 1 L cancels out, that's 1 minus 1 by L. L by L minus 1 by L times P squared minus expected value of x is P squared. So which means then that this 1 times P squared cancels out with minus P squared. What I am left with is 1 by L minus P squared by L, P minus P squared by L, which is equal to P times 1 minus P by L. Okay, that's our variance. So when I represent x1, if I generate a random bit stream for x1 of length 9 with probability 4 by 9, and I do generate this at random, then the mean will always be 4 by 9, but that's going to be the variance. Okay, so for large L, if I assume the product Y to be mean P1, P2, so this is the mean quantity, and just like the mean of x1 was P, and the variance of Y is going to be, just replace P here, P times 1 minus P by L by P1, P2 times 1 minus P1, P2 by L. Now as the number of bits in the unary bit stream, the length increases, the variance comes down. And if you think about for large L, and if you think about this as a Gaussian PDF, so y, if I think about that and plot the PDF, and that's going to be PDF with mean P1, P2 and standard deviation, which is equal to square root of P1, P2 times 1 minus P1, P2 by L. Okay, so usually you can take this quantity plus minus 3 sigma, but of course it's lower bounded by 0, can't go left. So that's kind of in the expected sense. So that's kind of what we would expect to be the output of an AND gate. So the output of an AND gate will compute. Sometimes the result may be here, sometimes the result may be here. It won't be exactly P1, P2. And that's important to remember. It will be in the stochastic sense or expected sense. It will compute expected value of x1, x2. So what happens if the input is an OR gate? So if I have an OR gate and inputs x1, x2, what does this compute? So what exactly is the expected value of y? So probability that y is equal to 1 will be probability that x1 union x2 is 1, which means that this is equal to, so if you take x, this is x1 and this is x2, and if you take the probability that this is x1 is 1, x2 is 1, so this is probability that x1 is 1 plus probability x2 is 1, so the union can be described as this plus that, then subtract the common part minus and assume x1 and x2 to be independent. Again, assume this to be independent. Then I can write that probability of x1 equal to 1 times probability x2 equal to 1. So the OR gate is really going to compute P1 plus P2 minus P1, P2, again in the expected sense. So it won't compute exactly that, it will compute that in the expected sense. So now we are getting a feel of how some computations can be carried out by these simple gates. If I had an exclusive OR gate, so in this case, probability that y is equal to 1 is probability that x1 equal to 0 and x2 equal to 1 plus probability of x1 equal to 1 and x2 equal to 0. Once again, assume x1 and x2 are independent. So then I can write this as 1 minus p1 probability of this times probability of that plus p1 times probability of that, which can be written as p1 plus p2 minus p1 p2 minus p1 p2, so minus 2 p1 p2. So if you look at the OR gate, the OR gate was computing p1 plus p2 minus p1 p2. The exclusive OR gate is computing p1 plus p2 minus 2 p1 p2. Okay, so now if I want to compute the output of a multiplexer, so let's have a multiplexer x1, x2 inputs, and I have a control bit x3, and let's say this is computing y equal to x1 if x3 is 1, otherwise it's equal to x2. So in this case, what would be expected value of y? Or so y would be, so let's assume that expected value of these quantities are p1, p2, p3. So the expected value of y would be p3 times p1 plus if this is 0 with probability 1 minus P3 times expected value of x2, which is P2. So that's going to be the value of the multiplexer. And finally, if I have an inverter and if I have input x and this is y, then expected value of y. So if this is 0, this is 1. If this is 1, this is 0, is going to be 1 minus p. So if this is 0, y is 1. If this is 1, this is going to be 0. If expected value of x is p, expected value of y is 1 minus p. So those are all simple examples of unipolar. We have been still talking about unipolar stochastic logic. We have not begun to talk about bipolar logic, which we will get to. Okay, so now let's talk about if I want to compute some simple functions. So let's say I want to compute y equal to x squared. Well, so if I want to compute y is equal to x squared, and I go back to that same example that I had here. So if I have the same example, and so what happens if I feed this 1 0 0 1 1 1 0 0 0 1 0 0 1 1 1 0 0 0, and believe it or not, if this is the same x, same thing, and of 0 and 0 is 0, and of 1 and 1 is 1, so this is going to be exact same thing. It is not going to compute. So in this AND gate, when both inputs are same and x and x, expected value of y will exactly be same as x. Why is that? Well, the reason I was able to compute the product x1 times x2 is because of the correlation or the lack of correlation or the independence. Now if I feed same x to both, now x1 equal to x and x2 equal to x are highly correlated. In fact, are so correlated that the correlation coefficient is 1. Okay, so rho x1, x2 is 1. And that is the reason the output of the AND gate is same as the input, which is p. So I cannot compute y is equal to x squared by just feeding x to both inputs of an AND gate, because it's just going to compute the same thing. So what is the solution to that? So the solution to that is you take the x to one input, but decorrelate by delaying this by one sample. So when this is 1 0 0 1 1 1 0 0 0, shift right by 1, and you can throw this 0 away, and then this becomes so in the clock cycle 2 I have 0 here, clock cycle 2, clock cycle 1. Okay, I could call this clock cycle 0, clock cycle 1. So in clock cycle 1 I have 0, so I don't throw this away, that's not what I said. Okay, in clock cycle 2, so I have 0 and that's 0. So now I have 0 0 1 1 1 0 0 1, and finally, so we have 8 locations. Finally, when this is 1, so here is the thing. So when it is 0 initially, this would really be holding something from the previous word, whatever the previous word was. I don't know what was input here. So this could be 0 or 1. The delayed value could be 0 or 1. I don't know what it was. So let's just forget that for a minute. In any case, 0 times whatever is 0. So if we see the product of this, 0 times 0, 0 times 0, 3 ones times 3 ones, and 1 times 1. So we will have 4 by 9. 4 by 9. So I guess something tells me that I didn't benefit from the decorrelation. Well, that's not looking good. That's not looking good. Let's see, something must have gone wrong. Something probably has gone wrong. So in clock cycle 1, we have 0 times 0. Okay. In clock cycle 2, 0 times okay, I see the mistake. Okay, so in clock cycle 1, this 0 is coming here. That 0, I see the mistake in what I wrote down. So this is going to be something I don't know. Then 0, 0, 0, 1, 1, 1, 0, 0, and that 1 will become part of the next product. So now if I take the product 0 times something, 2 zeros times something, and then 1 times 0, 1 times 1, 1 times 1, that's 2 ones, 0 times 1, 0 times 0, 1 times 0. So that's just 2 ones, which is 2 by 9. So 4 by 9 squared should be 16 by 81, which is 16 by 9 by 9. So it's about 1.8 by 9, and we get 2 by 9. So okay, that decorrelation at least works. Okay, so now how do I implement a simple function such as x minus x squared? So y is equal to x minus x squared. So this is x times 1 minus x, and I can implement that as x, take an inverter, which is 1 minus x, and then, by the way, if I just feed these to an AND gate to compute x times 1 minus x, the result will be 0, always 0. Because if this is 0, this is 1. If this is 1, this is 0. So you need to decorrelate, make them independent, and then put them into AND gate. That's going to be y. So it will compute what we need in the expected sense. If I want to compute e to power minus x, and then I can express that as a polynomial expansion, 1 minus x plus x squared by factorial 2 minus x cubed by factorial 3. Let's just take up to here. Let's take one more term, x fourth by factorial 4. We can stop with that. And then, so this will be, so you apply Horner's rule. So these numbers are 6, 24, and 2. So minus x cubed by 6 taken outside a bracket, we get 1 minus x by 4. And then from these two, x squared by 2 taken outside a bracket, I get 1 minus, then I get rid of that x cube, it becomes x, and get rid of this, that becomes 3. And then minus x plus x squared by 2, take minus x outside a bracket, and then 1 minus x by 2, the squared goes away, and finally 1 minus that. Okay, so that is the Horner's rule expansion of e to power minus x. And if I apply the stochastic logic to compute e to power minus x, then I can start with so our starting point will be 1 minus x by 4. How do I implement 1 minus x by 4? So this is x, this is 1 by 4, so that's 1 minus x by 4. So AND makes it x by 4, inverter makes it 1 minus x by 4. Okay, so that's done. And then minus x by 3, so this is multiplied by, so I need to multiply x, so let's say this is x, so x, and then 1 by 3, So 1 minus x by 3 times that whole thing, and 1 minus is by inverter, and then 1 minus x by 2 times that, so x by 2, and that x goes here and not, that's 1 minus, and then 1 minus x times that, so multiply by x and AND gate 1 minus that. So that's an approximate value of e to power minus x. And obviously this is not going to work as it is because of the correlation of x. So you should place a delays to decorrelate these things. So these are now decorrelated. So then I can compute e to power minus x by these 4 NAND gates. Okay, so that's how we can compute e to power minus x, and there are many more polynomials that we can compute as well. So one of the reasons why people have been, or in those days in 1960s, apart from low area, there was a lot of interest in fault tolerant computing. And in fact, ideas like triple modular redundancy by von Neumann were part of that process. A lot of the parts, computer parts, used to fail. So the idea of unary computing is if I have, let's say, that same 9 bit number, unary number, 1 0 0 1 1 1 0 0 0, and that value is 4 by 9. Now if somehow one bit flipped and became 0, then that value changes from 4 by 9 to 3 by 9. That's not a big jump. I mean, it's still approximately correct. It's not a big jump. But if I had a 2's complement number, okay, so I can't represent 4 by 9, but I should have a power of 2 in the denominator. But let's say that I had a 4-bit number or a 5-bit number like this. Okay, let's say this is unsigned. It doesn't really matter, but let's say it's unsigned. And if this unsigned number is, let's see, if I just take them on unsigned integers 1, 2, 4, 8, 16. So that's 16 plus 3, 19. And if this bit happens to fail, that value will change to 15. Okay, now what happens if this bit fails? The MSB, that's going to be 3. So depending on which bit failed, and particularly if, and what about this bit failed? And that's going to be 1. So that's going to be 16 plus 8, 24 plus 6, that is going to be 30. Now, so if I assume any one of these bits failing, the number changes a lot. 19 could become 3 or 30. So if any of the AMSBs or more significant bits fail, that's changing the value a lot. In the unary case, it's just changing by a small fraction, 1 by the length. And that was one of the more reasons why people became interested in stochastic logic and stochastic computing. So let me switch gears a little bit and talk briefly about bipolar stochastic logic. So now we will assume that each bit equal to 0. So when bit is 0, what is the value? -1. And the value here is +1. And the probability here is 1 is p, and this is 1 minus p. So, so if I draw the PDF, so the expected value of the number x is going to be 1 minus p times -1 plus probability p times 1, and that's going to be -1 plus p, and that's exactly what we talked about, which is 2p minus 1. Okay, so that's That's that. So let's see what are these gates computing. Now if I have an inverter, and this is now bipolar, so think about the inverter, but the inputs are, input and output are bipolar. Okay, so this is X, this is Y. Now what do you think will be the value of the inverter? So let's assume that okay, let's assume the value of the number. So expected value of X equal to P in bipolar. Okay, so if the expected value of P is in bipolar, then what will that be in unipolar? So the gate doesn't really care unipolar, bipolar. It just takes a 0, outputs 1, it takes a 1, output 0. So if this was in bipolar, the value was P, the so-called unipolar value would be 1 plus P by 2. Okay, we do know from the previous analysis the unipolar value will be 1 minus X. 1 minus 1 plus P by 2, which is going to be 2 minus 1 minus P, 1 minus P by 2. That means the bipolar value is going to be, what's the bipolar value of this? Multiply the unipolar value by P and subtract 1, multiply by 2, cancels out 2, so that's 2 times 1 minus P by 2 minus 1, which is equal to 2 cancelled out, 1 minus 1 cancelled out, and that's going to be minus P. Now surprisingly, if I feed a number, bipolar number, let's take that same number I had, which was 1 0 0 1 1 1 0 0 0, which was minus 1 by 9, right? So 4 minus 5 minus 1 by 9. Now if you take the inverter output 0 1 1, 3 zeros, 3 ones. So what do I get? 3 plus 2, 5 ones, 4 zeros, 4 minus 1s divided by 9, which is 5 minus 1, 5 minus 4 plus 1 by 9. So input minus 1 by 9, output plus 1 by 9. In general, bipolar input P, bipolar output minus P. So that's the output. So a inverter outputs 1 minus P in unipolar and minus P in bipolar. Okay, so let's briefly talk about if I had an exclusive OR gate. And let's say that bipolar inputs for X1 and X2 are P1, P2. Okay, so if the bipolar inputs are P1, P2, these will correspond to the unipolar inputs of 1 plus P1 by 2, 1 plus P2 by 2, which means that the unipolar output remember we already talked about that. That's going to be, we talked about the exclusive OR gate, which is really 0, 1 or 1, 0, which was 1 minus P1, which is now is 1 plus P1 by 2, times P2 plus P1 times 1 minus P2. So 2 minus 1 minus P1, 1 minus P1 by 2 times 1 plus P2 by 2 plus 1 plus P1 by 2 times 1 minus P2 by 2. Let's multiply these, so that's 1 by 4 taken outside a bracket, 1 times 1 minus P1, 1 times P2 minus P1 P2 plus 1 times 1 minus P2 plus P1 minus P1 P2. So let's see if anything cancels out. I see that minus P1 cancels out, plus P2 cancels out. So we are left with 1 plus 1, which is 2, minus 2P1 P2. So 2 taken outside a bracket, 1 minus P1 P2 by 4. And I can cancel the 2 with a 4, which is 2. So 1 minus P1 P2 by 2 would be the unipolar output. And the bipolar output would be 2 times this minus 1. 2 times 2, 2 cancelled out. So 2 times 1 minus P1 P2 by 2 minus 1. 2 cancelled out. 1 minus 1 cancelled out. And that's minus P1 P2. So the bipolar XOR computes an output that is the negative of the product, which means that if I have a bipolar XNOR, that computes this is bipolar XOR and this is bipolar XNOR, and this will compute the negative of that, because we saw the inverter computes minus P. So if I just put inverter, this will compute, Y will be, expected value of Y will be P1, P2. So the bipolar product, unipolar product can be computed by an AND gate. The bipolar product can be computed by an exclusive NOR gate. Okay, we are talking about bipolar. So let's go through we'll talk a little more about how to analyze these gates in different formats. But let's spend a little time talking about inner product, because that's really what digital filters are computing at the end. So if I compute So I want to compute an inner product. Y is equal to A1, A2, X1, X2. So that's the inner product of the vector A and the vector X, which is A1, X1 plus A2, X2. What is the easiest way to compute this? First of all, we have to always make sure that this sum, if this sum has to be bounded between minus 1 to plus 1. So instead of computing, or in case of unipolar, between 0 and 1. So instead of computing that, we can compute Y prime is A1 by A1 plus A2, X1 plus A2 by A1 plus A2. So we are scaling by factor A1, A2, and that scale factor will make sure that there is no overflow. And the way we can compute in unipolar, so if I want to compute the inner product in unipolar, let's see what I can do. I can take a multiplexer and then have a control signal. So the inputs are X1, X2, and I set the control signal X3 such that expected value of X3 is equal to A1 by A1 plus A2, and then if X3 is 1, then we multiply with X1. If X3 is 0, and that will be 0 with probability 1 minus that, which is A2 by that, and that's going to be Y prime. Okay, so that's how we can compute the inner product in unipolar. How do I compute the inner product in bipolar? So I can write down y prime is equal to A1 So let's assume that sine, so A1 is greater than or equal to 0, means the sine is 1. So sine of A1 is 1, and if that's negative, sine of A1 is 0. Okay. So A1, so in bipolar, let's start with the value of A1 x1. So how do I compute a product A1 x1? So if I start with A1 and x1 and have an exclusive NOR gate, that's A1 x1. And similarly A2 x2 okay, and then if I feed these to a multiplexer such that, so we want to compute so if I feed, let's see, y prime, okay, let's try to feed x3, let's try to feed, okay, so x3, expected value of x3 is equal to absolute value of A1 by absolute value of A1 plus absolute value of A2. Okay, so I think let me start writing these. Let's start writing these slightly differently. So y prime, so instead of writing down y prime equal to this, so we will divide by, instead of A1 plus A2, so let's see, y prime becomes A1 x1 by absolute value of A1 plus absolute value of A2 plus A2 x2 by absolute value of A1 plus A2, which can then be written as, we'll come back to that, but it can be written as, so y prime, so by the way, A1, I can write A1 is equal to sine of A1 times absolute value of A1. Right? So if A1 is minus 5 by 8, as an example, sine will be minus 1, absolute value is 5 by 8. Okay, so so then I can write y prime is equal to A1 absolute value by A1 absolute value plus A2 absolute value times sine of A1 times x1. So we have replaced A1 by sine of A1 times absolute value of A1 times x1. This stays as it is, plus A2 absolute value by A1 plus A1 absolute value plus A2 absolute value times sine of A2 times x2. Okay, so now if I think of this as a control signal value x3, so that's my x3, okay, expected value of x3, and this is going to be 1 minus. So if I want to compute, if this is 1, I want to input sine of A1 by x1. So I want to input sine of A1 times x1. So feed sine of A1 to the exclusive NOR, sine of A2 to the exclusive NOR, and finally I get sine of A2 times x2. And this is 0, which means that the probability of selecting this part is going to be A2 by that multiplied by sine A2 x2, and this is going to be the y prime that we are computing. So that's going to be the bipolar implementation of the inner product. So this is really a very brief intro to stochastic logic. We can spend a little time talking about some of the papers that I have asked you to read. Okay, so let's just try to see if I can walk through some of the papers, and then let's just take a look. So first of all, the first long paper, very long paper that you don't have to read the whole paper. We just want to get an idea. But let me see. So this paper in the conference is really my class notes. So if you think about, this is a review paper. So let's just take a look at, so I would say you start with this paper, Fundamental Computational Logic in Stochastic Logic, AND gate, OR gate, NOT gate, XNOR gate, and MUX gate. Okay, so those are gates that we want to see what they are computing. Okay, we talked about how to compute AND gate, how to compute OR gate. So this paper is really nothing but my lecture notes from the time I taught previously, and so I've walked you through these steps, computing the multiplexer output. So I've walked you through the section 2 for the unipolar, and this is bipolar, how to compute outputs of bipolar NOT gate. So this is exactly same thing that I talked about bipolar multiplexers. So the last section is really what I didn't talk about. So we can quickly walk through that, how to analyze complex bipolar. No, I probably did talk about that. Okay, I didn't. Okay, so this is really your homework. That was homework for the class that I taught last time, and now that's part of this paper, the homework that was handed out. So your homework is solved here in a way. By the way, this table 1 shows for these 5 gates that we saw, AND, OR, NOT, XNOR, MUX. Unipolar input and output, unipolar input, unipolar output. Bipolar input and bipolar output. And then there is something called hybrid. What would really the output be if the input was unipolar, output was bipolar? And here in the last column, bipolar input, unipolar output. Okay, so let's talk about how do we analyze these complex gates. So this is a simple circuit. There is a delay element. You can ignore the delay because that's just decorrelating the Y input from the first gate and the second gate. So we have an OR gate that's fed to an AND gate. How do we analyze this? Well, how do we analyze this in unipolar? The unipolar should be easy, right? So the unipolar, if I look at the expected value of N1, we already saw for the OR gate, that's the probability of union of x and y being 1, which is px plus py minus the common part that was double counted by adding px plus py. The AND gate is simply computing that times y. So that is the output in the unipolar input, unipolar output. To compute that in bipolar, so we start with, so I have already computed the unipolar output. So the bipolar output F is 2 times the unipolar output minus 1, which is 2 times this quantity minus 1. This is, remember, this is unipolar. And now I need to input what are the unipolar values of x and y. If it so happens the bipolar value of x was lowercase x, then the unipolar value would be x plus 1 by 2 plus y plus 1 by 2 minus the product of these two times 2 times probability of y is y plus 1 by 2 minus 1. So that's how we compute the output F in bipolar signals. If x and y are input in bipolar, that's the output. If x and y are input in unipolar, equation 12 is the output. Okay, let's see what else we can compute. There is a second approach, you can read that on your own, leading to the same result. So here is another example in figure 3. So we have 3 gates now instead of 2 gates. There is a NAND followed by an OR followed by a 3-input NAND. Okay, what is this computing? So first of all, this first NAND computes 1 minus xy. 1 minus xy, that's right here. 1 minus pxpy. Then there is an OR gate that has the input y and 1 minus xy. So that output is going to be y plus 1 minus xy minus y times that. So a plus b minus ab. That's output of OR gate. And finally, we multiply that by okay, so you may wonder why I am computing this by times 3 by 4. So this is really a very tricky part here, because you think about, so I am interested in computing the result F in terms of xy in bipolar logic. So the value of this coefficient half is in bipolar logic, which means in unipolar that's going to be 1 plus half divided by 2, which is 3/4. I'm now computing everything in unipolar. So we have to convert x, y and half to unipolar. So that's times 3/4 and 1 minus that because of the NAND gate. So that whole thing is the result in unipolar. Note that the coefficient half needs to be converted to unipolar. If you didn't do that, that's going to be a mistake. Finally, we need to substitute these values px and py, which are x plus 1 by 2. If x is in bipolar, that unipolar value is x plus 1 by 2. Output y is going to be y plus 1 by 2, and you go through that whole equation and simplify, that's the result. I believe that's your homework. So there is a second method as well of computing that, and I will leave that to you. Okay, I will leave that to you to read. So that's kind of, that's a good paper to read. And this second paper to read is this paper we talked briefly about. This paper is all about unipolar using stochastic logic by series expansion. And we are expressing these approximations of sin x, cosine x, tan hyperbolic, and so on sine pi x. There is a lot in the paper. I don't really need you to read all of that. But I think it's useful to read how we are applying the Horner's rule. As I, again, the paper came out of my teaching in the class. So, I briefly talked about how to compute e to power minus x. So maybe the best thing might be to read, let's see, this section 3. So maybe there is no real need to read the whole section. Read just section 3, how we compute sine x, cosine x, tan hyperbolic x by expressing by Horner's rule and then computing circuits from that. So it is useful to read section 3, part of section 3, not even the whole thing. I don't really need you to read the whole thing. There is a lot in the paper. There is a lot. Some of these diagrams are illustrating if I want to compute e to power minus 2x, and I already know how to compute e to power minus x, then just feed that into an AND gate with a decorrelation by a delay, that's e to power minus 2x. And similar examples here, computing e to power minus 10x in different ways. So I'm going to, I don't really need you to read beyond what I talked about in the class. And let me see the other paper that came out of teaching last time in the class. In fact, this paper came out of the homework that I've given you, I believe. Okay, so what I am trying to describe here, excuse me, not this paper, the other paper. So in this paper, I am trying to assume the case when the stochastic logic polynomial has all positive coefficients. And I am trying to describe how to expand these kinds of polynomials using unipolar logic in several ways, probably 3 ways, maybe 4 ways. So I think I would start with section 3, so e to power x minus 1, and how we are expanding these in different ways. So there is tree structure expansion, ascending order, so I express ascending order. So I first take the first 2 terms, then group the next term, then group the next term. And then the descending order. So this is a descending order. So I expand. This is expanded by using Horner's rule, as I have talked about in the class. Maybe it may be useful to just read this one approach instead of many approaches. Section C would be useful, I think. So start with the Horner's rule approach and see how that maps to this figure 5, e to power x minus 1, using Horner's rule. So there are several expansion approaches. All of them are equivalent. So for example, figure 5 and figure 6 are showing same thing, but with 2 different circuits, one obtained by Horner's rule, another by so-called OR and expansion. So there are many ways of, there is AND or expansion. There are 3 different ways, so I don't need you to read the whole paper, but read at least one method. Maybe read the Horner's rule method, which would be this subsection C. Okay, so that's a brief intro to stochastic logic. It has a lot of applications. I am not going through a lot of those in the class, but it can be useful in several applications beyond electronic computing. And in fact, this is an idea that we applied in DNA computing that turned out to be very, very useful. And in particular, these delay elements that we are using to decorrelate didn't really need to be decorrelated like this in the DNA computing or molecular computing. So there are people using these kinds of ideas in spintronics in the context of magnetic systems, magnetic computing systems. So we are not going through a lot of those details, but it is probably sufficient to know the background. So why didn't the electronic computing systems adopt this? It so happens that to really make these systems practical, you need a very large length. As we saw, the error of the variance of the number is inversely proportional to L, and I can reduce the variance by increasing L. And the moment I increase L, the bit stream length increases, which means that the energy consumption increases a lot. So it may be that the energy consumption of AND gate or multiplexer, whatever, is a small number. But if you take a 1000 bit stream, then the energy consumption of that operation have to multiply by 1000. That's where the problem is, and the energy consumption is a lot. And so while suitable for low area implementations, these are definitely not low energy computing systems. Okay, so I will stop here today. So the class has ended and the semester has ended. The exam will be on Monday next week. Okay, see you.